Hello everyone, welcome to ME231 Undergraduate Solid Mechanics. I'm Sungwar Yu, who's gonna give lectures on this course for spring 2021 semester. So I'm not sure about how situation will evolve about the COVID-19, but if the COVID-19 somehow resolved in the middle of spring semester, we may see each other in person. But if not, yeah, we might have to rely on this online lecture. But still, let me try to give you the best lecture that I can give you in this semester. And because probably for most of you, I think most of you are like a sophomore who declare mechanical engineering as your major, and I'd love to offer a lecture that can meet your expectations. Okay, so some of you may wonder, okay, this is solid mechanics, and you might think that okay, back in freshman physics, I have already learned about mechanics of solid, okay, and you also learn about mechanics of fluid a little bit. So I want to open the lecture by comparing the uh, difference and similarities between freshman physics and ME231. Okay, so this is the table that summarizes what was going on in freshman physics and what you're gonna learn in ME231. So the object of the study in freshman physics was rigid body, but in ME231, we're gonna learn about deformable body. So some of you who went science high school or genius high school, or whether even though you go to just regular high school, you should have learned about some mechanics. And until now, the mechanics you have learned considers rigid body. However, in real life, there is no rigid body. Actually, all the body in world actually is deformable. Okay, so the object we're gonna deal in emitter I would say it's more realistic. And about the loading mode, back in freshman physics, you only learn about like a tension and compression, a little bit of torsion. But ME231, we're gonna learn about tension, compression, bending, and shear and torsion. And I'm gonna tell you what are these. Okay, so we'll learn about how deformable body would deform under tension, compression, bending, and shear and torsion. Then we have to also think about physical quantities. So back in freshman physics, we learn about pressure, force, and displacement and torque. And pressure is a scalar quantity, and force, displacement, and torque are vector quantities. In addition to these quantities, we learn about stress and strain in ME231. Okay, so this is like a one table summary of the difference and similarity between freshman physics and ME231. So what will be the goal of ME231? Yeah, so I would say the goal of ME231 is like a design of mechanically reliable structures and cars and ships. So in 9 p.m. news or 8 p.m. news, you might have seen a lot of accidents on structures and airplane and bridges and cars and ship. So if you don't do the design properly by considering this mechanics, you might expect to see huge accident and sacrifice of a lot of people. Okay, so this lecture will give you the basis of all those mechanically reliable design knowledge. Okay, so let's begin from the first topics, object and loading. So let me give you a little bit more detailed discussion on these object and loading modes. So what's the definition of rigid body? Let's start from the rigid body. So rigid body is an object in which deformation is neglected, or in other definition, you can say that for rigid body, the distance between any 2 points remain constant in time regardless of external force. Okay, so these are the assumptions we made about rigid body back in high school physics and freshman physics in your freshman years, but everybody knows that this is not real. Okay, so we'll talk about real deformable body. Okay, so here's the question: is a rigid body exist in real world? Of course not. Okay, and about the loading mode, let me give you some highlights. So the loading mode we're gonna consider in ME231 is following. So maybe back in freshman physics and high school physics, you might only learn about this thing like a tension or compression. This is axial loading. But in addition to axial loading, what you're gonna learn is shear loading, shearing force, where you can bend the beam in this way, or bending. So you are take like your erasers or any papers, so that if you give some torsion on two ends of your paper or eraser, you're gonna see your object will bend. And another thing is torsion. This is when you have this circular object and try to twist this circular object, you see that starting from here you're gonna see twist of the body. So okay, so these are the loading modes we're gonna consider in ME231. So first we'll go through this loading mode one by one, like separately, and in later chapters, maybe chapter 8, we'll try to analyze the structure on the combined loading, like combined torsion, combined bending moment, like combined shear and axial loading, and combined loading of all. Okay, so after this loading mode, regarding the each material element, I mean if we focus on this little body, like this little body outside of this out of this object, we can separate stress in these three modes: tension and compression, shear. So macroscopically we can say torsion, bending, and shear and axial loading. But if you focus on this little tiny body, you can decompose the loading of this infinitesimal body as tension, compression, and shear, and we'll call this as stress we're gonna analyze. Okay, so I'm gonna give you the definition of stress soon, but if I just say stress in a very short word, it can be said as force per unit area. Okay, so we'll go through the definition of stress soon. Okay, so you can already see that in addition to the difference in object, you can see that we're gonna discuss about much more variety of loadings. Okay, so see much more variety compared to high school physics and freshman physics, where you mostly deal with axial loadings. So what you're gonna do is following. So without learning ME231, even though you only consider rigid body, you can get NMVT. So N is the so this is the notation we're gonna use. We're gonna use N for axial loading in our class, and V for shear force, and M for bending moment torque, and T for twisting torque. Okay, so without assuming deformable body, and if you only rely on Newton's law and action reaction principle, you can obtain NVMT. Okay, so this is what you're gonna do. So what we can do already from freshman physics. So in addition to these knowledge, what you're gonna do in ME231 is, starting from this NMVT, so this is two forces and two torque, we'll obtain normal stress, shear stress, and shear stress. And out of this shear stress, we're gonna obtain a so-called strain, normal strain, and shear strain and shear strain. And out of this strain information, we're gonna obtain the deformation of the entire macroscopic structure. And out of this deformation information and out of this stress information, we'll predict failure of the body. Okay, so when we predict the deformation, this strain is I would say displacement per unit length. So this is connected by material property called Young's modulus, shear modulus, and Poisson's ratio, or if we call everything, we call that as stiffness. Okay, so we'll obtain deformation by connecting stress and strain in this ME231 course, and we'll predict failure by comparing the stress and applied on each body, by comparing these stress with the strength of the material. I mean, strength is the maximum stress that each material can sustain. Okay, so without giving the definition of stress and strain, I'm telling you too much. So from now on, let me give you the definition of stress and strain soon. Okay, so as a second topic, so I I gave you one table summary of the difference between ME231 and freshman physics. So regarding the object and the loading modes, we already had a discussion. So let's move on to the physical quantities. Okay, so before talking about the definition of physical quantities, let me opening up this discussion. So I want to discuss about the necessity of defining so-called stress and so-called strain. Okay, so in addition to stress and displacement, which we have already used in freshman physics and high school physics, when we define the spring displacement, when we define force acting on the pulleys and all those problems, why do we have to define stress, which is a force per unit length, strain, which is displacement per unit length, for our course? So let me give you some example. So here we're gonna consider two examples. So here we have material A and material B, but their dimension is different. Even though their length is the same, 50 centimeter, their diameter is different, 5 centimeter and 10 centimeter. And we found that after this tension experiment, the cylinder A failed at 50 kilonewton, but cylinder B may fail at 60 kilonewton. So out of this experiment, we found that the failure force for this B cylinder is larger than failure force for this A cylinder. But let me ask you this question: is material B is stronger than A? I'm talking about material itself. Okay, if somebody asks, is cylinder B stronger than cylinder A? Yeah, we can say yes. But if other guys say if material B is stronger than material A, we would say of course not. Okay, so the comparison we can make is if you make cylinder out of steel with diameter of 1 nanometer, and if you compare the same length cylinder with your rubber eraser with a diameter of like a 10 centimeter, of course your rubber eraser will sustain much larger force, right? However, if you compare at I would say fairly, you can of course see that steel is stronger. Okay, so stress is necessary for making fair comparison, right? So the second question I can ask is this a fair comparison? Of course not. Okay, so what we have to do is we have to compare force per unit area. Okay, and because of that, we need the definition of stress. Okay, so there is two kind of definition about stress. So if you consider these kind of stress where force is acting orthogonal to this cross-section area, we call this as like a normal stress, and we define this as F over area A. If you add your force in parallel to this cross-section area A, then you define this as shear stress. So there is two kind of stress. Okay, so normal stress and shear stress. So now we have understanding on the necessity of the stress definition. Now let's move on. So the second example that I'm gonna give you is will explain the necessity of a strain. So here we're gonna compare this blue colored cylinder and green colored cylinder, and they have the same diameter but they have different lengths. Okay, so the left one has 50 centimeter and second one, right one has 100 centimeter, and we found that they are sustaining 100 kilogram gravity weight, and the displacement for first one is 5 millimeter. Displacement for second one is 6 millimeter. Okay, so we found that cylinder C deforms less than D. Okay, now somebody would ask, is a material C stiffer than D? And then even though material this left cylinder deforms less than right cylinder, we cannot say material C is stiffer than D. Okay, yeah. The definition of stiff is it's hard to make a deformation. Okay, if you compare steel and rubber, of course it's much harder to deform steel, and we call steel as stiffer than rubber. Okay, so here the left one deforms less than right one, then the cylinder itself will be stiffer than cylinder in the right. However, if somebody asks the question, is material C steeper than material D, we would say no. Okay, and if somebody say, is this a fair comparison, we're gonna say no. Okay, so we should compare displacement per unit length. Yeah, this is very important. So when you compare the stiffness of two different material, we have to compare, to make a fair comparison, we have to compare displacement per unit length. Okay, and if we define the displacement along this length, we call that as normal strain, delta L over L. And if you consider displacement in lateral direction, we call that as shear strain. Okay, so this is the necessity of the definition of stress and strain. And after defining stress, after defining strain, one can define the material property. Okay, so out of these two examples, what one can see is, without defining normalized force, without defining normalized displacement, one cannot compare the material property. Okay, so for example, if you want to compare the material property between wood, rubber, steel, you should make you should make a comparison between in terms of stress and strain curve, not just like the entire force and entire displacement. If you make a material property and define material property in terms of force and displacement, your material property will be size dependent. And if material property is size dependent, you cannot call that as a size material property. Okay, whether you consider like a huge steel rod, whether you consider like a steel rod with as big as your hair, the material property should be same. Okay, so that's why we define stress and strain, and by measuring the relationship between stress and strain, one can define mechanical property of material. Okay, and this is typical stress strain curve. Okay, so if somebody make a sample in cylinder shape and try to make a tension experiment, and he defined stress as F over A and strain as delta L over L. The original length is L, and if you compare the relationship between stress and strain, originally it will have a linear relationship. We call this slope as modulus or stiffness of material, and at some point when stress touches some maximum, the material will start to fail. We call that as strength. The maximum stress out of this stress strain curve is called the strength. Okay, so please make a distinction between strength and stiffness. Stiffness refers to the initial slope, strength refers to the maximum stress value. And even though it starts to have some sort of a crack or necking, it will still sustain a little bit of displacement and completely fail at some point. Okay, so this is typical stress strain curve, and please make a distinction between stiffness and strength. And if I tell you one more thing, if we make this area, we call that as toughness modulus. Okay, so when somebody say material is tough, when somebody say material is strong, when somebody say material is stiff, it tough, stiff, strong refers to different meaning in material property. Because you are now taking ME231, you have to make a distinction between toughness, stiffness, and strength in your life as an engineer. Okay, so hopefully this gave you some idea on the difference between freshman physics and ME231, and hopefully this gave you some idea on why do we need the definition of stress and strain. Okay.